Hey everybody, Mr. Bowman here. Another video on 3.13 probability concepts. In this video, we're looking at all the excellence questions for the 2019 exam. Let's get straight into question number one. Question number one. This one's a bit weird. This first one is kind of relevant because it helps us explain this excellence question later on. But let's get into it and answer both of them. So we've got a school roll, a New Zealand provincial primary school. We've got years 0 to 8. The data we have, it looks like it's going to be based on age and gender as at 1st of April 2018. All the data summarized below. There we go. So we've got the 343 students. We've got some information on the females at the school. We've got some information on the males at the school. And the principal has used the data to predict the new students enrolling at the school, and specifically is trying to predict how many of them are going to be male, calculate the proportion using this data to support the principal's decision. So this one here was really easy for triple I. It asked you basically to find out, what's the probability of it being male. So we know there's 343 students in total. We actually weren't told exactly how many of them were male. We were told the exact female number, but not male. But if we go 343 minus the female number, which we were told was 149, remember that's up the top here, that's going to get you the total male number. You can plug that into the calculator, go straight to a decimal, but our decimal was 0.5656, and that there had a 4dp rounding. So I guess the principal would have made a prediction like that. So that's triple I. Now we're now going to move on to IV, which is where the excellence mark comes from. So give two reasons why care should be taken when using the data predict new student enrolling at the school will be male. So we made the prediction here. So why should we hesitate in using all the information above as a reliable estimate? Okay, I'll move that around. We're going to get into the question. So give two reasons. So the first thing is when you're looking at the data, there was a few clues here. And we actually underlined some of them as we're reading the question, which is nice. So the first thing to note was this school rule was based on one provincial New Zealand primary school. So it's based off one school, might not be valid for every school. So that's probably the first paragraph I'm going to have. The next bit of information, this data was valid as of 1st of January 2019, and 2018. And this wasn't the 2019 exam. So in that 6 months between 2018 and where the data was collected in the 2019 school year, is there going to be any change for whatever reason? So I think the date is going to be the other issue. So I'm going to probably talk about these two ideas. So these are going to be the two reasons I want to talk about. And what's going to be really important is, as I do this discussion, I want to explain why using it might be wrong. So I want to give an example based on the context of the question. So I guess the first starting point was, so the data used to determine the above estimate is from a specific provincial NZ primary school. So that's the first issue I've got. And I think predictions based off this may not be valid for other schools. So predictions or estimates based off this data may not be valid for other schools. So that's going to be the really, really big part. This data is very specific to one school, might not really be relevant. And then I want to link it to the proportion of males. So the proportion, forgive me my bad typing, proportion of males at one school may be different across schools. And there may be a whole bunch of reasons it may be different. It may be the program of the school. It may be the proximity of nearby schools. And that might impact where parents are sending their sons. So the example I've got, and that's because I work at a boys' school. So, for example, this is a co-ed school, but let's say down the road is like the best boys' school in the country or the best boys' school in the world. Of course, parents are going to want to send their sons or their boys there, and that might mean the boys we have here, it's actually lower than what we would have expected because a lot of them have been attracted to that other school. So, for example, if a community has a really good boys' school in it, I would expect the proportion of males at nearby co-educational schools to be slightly lower. So what I'm really just saying is I'm saying if there's other schools that are really good and nearby, that might impact the decisions they make, and that means the data we've got for this school might not be valid because the school in another city is going to have other schools that are nearby and they may be different, etc. So hopefully that school stuff makes sense. I've just edited it slightly to give me more room for the time one. So the time one is assuming the kind of the trends in education are kind of consistent from the date this data was collected in 1st of July 2018 to the beginning of 2019. Because, for example, you see on the news all the time that, co-ed schools are amazing for this reason. And then, the next year it's, girls' schools are all the rage. And then the year after that, boys' schools are all the rage. So the fact these different studies, different surveys are really impacting the trends that we see in education may influence where the boys or the males in this case are going. Maybe at this time they said co-ed schools are the best for the boys, so all the parents are going to send them to the co-ed schools. And then maybe next year, maybe late 2018, the new research shows that boys' schools are the best, so now they're going to send them off to the boys' school instead. So that might slightly change what parents are going to be deciding here. So let's write up our one. So the data used to determine the above estimates is from a specific date. In this case, the dates being 1st of March 2018. Also 2018, they wrote 28. Using data from 2018 to make future predictions may not be valid as trends in education may differ over time. So that's exactly what we talked about maybe later on in the year, boys' schools are all the rage, and everyone says you should go to boys' schools instead of co-ed schools, and that might impact where these boys are going in the community. As a result, the probability of a male at the school may differ as the popularity, or I can't spell popularity by the looks of it, or unpopularity of boys' schools changes over time. So let's fix that. I'm too OCD to leave that there it is. So hopefully that makes sense. I've given 2 reasons, and I've tried to link it back to the data that we're looking at here. Okay, we are now on to question number 2, and this does carry on from the kind of the school stuff that we talked about before. So it is generally assumed that 50% of primary school students are male. Makes sense by the fair assumption. The principal of the provincial primary school referred to in part A thinks that based on their school sample of students in the region, the proportion of male students in the region is greater than 50%. So they reckon there are more than 50% of males in their school. And that makes sense because if you remember in the previous video, or the previous question, the proportion of male was 0.5656. That's kind of roughly 56%, 57%, which is quite high. Discuss how carrying out a simulation would help the principal consider whether their students, as a sample from the region, would indicate that the proportion of males is in fact greater than 50%. And it says you don't need to design a simulation, you just need to talk about what a simulation would result in. So a simulation, hopefully you remember this in class, but the idea of a simulation is you're expecting to see the natural variation that occurs due to randomness. So I probably want to do 1 paragraph discussing the variation that the principal might see and what that might mean for his school, etc. Once you've got your simulation, you then probably want to compare it with your observed data. So we've got the observed data of 56%. So the principal would want to actually make a comparison, like how far off is that number? Does it make sense, etc. And then once you've done that, we're probably going to do a 3rd paragraph just linking it back to the principal in his context. So this is kind of the structure that I want to follow for this particular question. So I'm going to do 3 paragraphs on it. It might be a bit long, but there we go. So I guess variation, the idea of the simulation is if we're assuming, like they said up the top here, 50% of the males, 50% of the kids are going to be male, we're going to see the variation that would naturally occur in a school roll of 343 students, which is what this principle had. So let's start going. So a simulation based on the assumption of 50% males would allow the principal to see what variation in males he would expect to see with a school roll of 343. So that's kind of the thing. So for his school, how much variation in the proportion of males is he expecting to see? So once he's got that variation, he then wants to kind of compare it with his numbers. So that's what this observation comparison part means. So the principal could then compare these simulation results with the actual data of 194 males, and that was being 56.56%. And then following that, he could do that. So once he's got the actual data and he's made the comparison, so once he's got the simulated data, he's making the comparison, he's then going to be able to assess, how likely was it for him to have 194 males? Like, was it just a freak? Did that natural variation happen every so often? In which case it's okay, and it's probably just due to randomness, and that means maybe there are 50% of the community are males. Or if the data is really, really far off, it probably means there's more males in the community. So the principal could then use this to assess the likelihood of the school having 194 males and whether or not the community or the region, they've used the word region, has greater than 50% males in it. So that's ultimately what he's doing here. So he's going to see the variation. Once he's got the variation, he's going to be able to compare it and make some decisions. And based on that, he can then make a decision. So if all of the simulated results, so maybe he's going to do 1,000 simulations, and if some of them are greater than 194, or if he's got a few of them around 194, then that probably tells him that this is just okay. It's just due to randomness. He's got heaps of males at the moment, but due to the randomness of these things, it'll go back and forth in subsequent years. So that's the first thing we could do. So if the simulation shows results around 194 or above 194, the principal knows the current roll of 194 males out of 334 is due to expected variation of a school with 50% males. And the opposite of that can be true. If we don't see any simulations that are near that number, then we know maybe there's something to his theory about there being greater than 50% of males. So if the simulation does not show any results near 124, then there may be evidence to support the principal's idea that the region has greater than 50% of males. So that would have been my answer. So when I checked the model answer to this, I did go in probably a bit more detail. So this last paragraph, they didn't really talk about it too much, but I thought it was really relevant to what we're doing here. And I thought it was a great way to link my first two paragraphs with the context of the question and the decision that the principal is trying to make. We are now on to question number 3. The link to all these questions is in the bio to this video, so have a check, or check them out if you haven't seen the link and other excellence questions. So it is suggested that snoring, so you might remember the snoring stuff from all the merit videos, has an impact on the student's performance in examination. The data was collected on whether or not a group of year 13 students got achievement. So they either, passed or didn't pass the assessment. It was found there were 123 snorers, 91 of them got achieved or better. There were 78 non-snorers, 68 of them got achievement or better. For students who snore, 32% of them complete homework tasks. For students who don't snore, 65% of them have homework tasks. Suppose 3 students were selected at random, so that's going to be interesting. 3 students selected at random. Calculate the probability that all 3 students don't snore and always completed home tasks. So we're trying to find the probability of they don't snore, so S dash, and they did all the homework tasks, so S dash and H. So it looks like it's going to be a probability tree to find this probability. And then once we've got it, we then have to consider the impact of the 3 students. But let's worry about that bit of it later on. So the first split, because we'll try to figure out people who snore or don't snore. So the first split is going to be the people who snore and the people who don't snore. And we've got the probabilities here. We had 123 snorers, 78 non-snorers. That's 201 people in total. So we're going to have 123 over 201 is the probability of someone snoring. And then we got 78 over 201, which is the probability of someone not snoring. Now that we've got that, we're splitting them off based on whether or not they do their homework or not. So that there would be the homework group, and these H dash, the people who don't do their homework. And then we've got the homework people and then the not homework people. So this is when the numbers up here. So this 32 number here. So 4 students snore, 32% of them complete their homework tasks. So that means the H1 up here, that's going to be 0.32, which means the number below is going to be 0.68. The next number, 4 students who snore, 65% of them complete their homework tasks. So that's interesting. The snorers are more likely to complete their homework. So that there is 0.65 and down the bottom is 0.35. And as we said, we're trying to find the probability that someone doesn't snore and does their homework. I just realized I got the other way around. So the snorers do their homework a lot more than, the not snorers do their homework a lot more than the snorers. So this one here, so this is the probability of not snoring and doing their homework. And that's going to be equal to 78 over 201. And we're going to multiply that by 0.65. And when you do that multiplication, you're getting 0.2522. And that they had a 4DP rounding. So I've now got the probability, and I now need to figure out how that relates to 3 students, not just 1 student. So the probability that all 3 students, are not snorers and do all their homework, it's going to be that number cubed. And when you do that math, that's going to get you to 0.0160, and that they had a 4DP rounding. So that was this part of the question here. We didn't actually read the last part. Support your answer with statistical statements, which I think we've done already, including any assumptions made. So that assumption one is a really biggie. Okay, so I'm just going to type up the answer here. So because we're cubing it, the calculation assumes that the 3 people, their snoring and their homework habits, it does assume that they are all independent of each other. And that may or may not be the case, because if you're picking maybe 3 students from a group of friends who hang out in the library, for example, I feel like those students are more likely to be doing their homework than perhaps the students who are elsewhere, maybe not up to any good. So let's get that. So this calculation assumes that the snoring and homework habits of all 3 students is independent. So that's the assumption we've made. It's often good to kind of critique the assumption that you've made. So I think this assumption might not be a valid one, and we've already identified why. So this assumption may not be valid as a group of friends may study together, and as a result, their study habits may not be independent from each other. So yeah, we made that assumption. Probably not the best assumption. I've spelled there wrong and I spelled friends wrong. There we go. But we have made that assumption. Okay, so we are now on to question number 4 from all the questions on the website. And just a note, don't answer I for this question. That just had all the assumptions we needed. So make 2 comments about the validity of the assumption made that the year 11 students who snore have the same risk of not achieving as the year 13s who snore. And that assumption kind of came from the previous question up here. Okay, so when thinking about it, if you read the question above here, the first half of it talks about the same risk of getting a not achieved as the year 13 counterpart. So it kind of assumes that getting a not achieved for year 11 should be the same as getting not achieved for the year 13. So let's start thinking about my answer. So assumption number 1, we've actually assumed the probability of getting a not achieved given your year 11. We've actually assumed that's going to be the same as the probability of getting a not achieved given your year 13. And I'm not sure that's a good assumption because it kind of means year 13s and year 11s are all passing and failing at the same rate, which from my experience as a teacher, maybe your experience as a student, maybe that's not a fair and valid assumption. Okay, assumption number 2, and this relates to the next bit of the question, it kind of also has the same assumption, but to do with the snoring. So it assumes that year 11s have the same likelihood of snoring as the year 13s, and the same as the not snorers as well. So it's assuming that the probability of snoring given their year 11 is the same as probability of not snoring, so S dash, given they are year 13. And as I said, I don't know if that's a good assumption either. Just noting, carrying on with that, that also means we've assumed the probability of, so I've got this dash here wrong. So this one here, we're assuming the probability of snoring is going to be the exact same between the year 2 year groups. And this one here, we're also assuming that the probability of not snoring is the same between the 2 year groups. So we kind of made 2 assumptions in terms of our calculation. So I've tried to be quite mathy with my assumptions this time around, and we're going to talk about them in a bit more detail. So the first assumption relies on the year level, same passing or failing. And I don't think that's a good one either. So I think that the main reason being, I think in a year 11 class, you're probably going to have a more diverse range of students in that classroom because perhaps people who struggle with school, they're probably still in school in year 11, but by the time year 13 comes around, maybe they've gone away and tried to find an apprenticeship, or they've gone to a Unitech course or something like that. So I found from my experience as a teacher, the year 13 classes are a lot more serious about it, and that's probably because they're trying to get into university, and the people who maybe didn't take school as seriously are probably left by then. So let's start writing that. So year 11s may not be as smart as the year 13 class. And then I'm just going to say on average. And that's really due to their age, isn't it? Due to their age. So the year 11s, their brain literally isn't developed enough, so it might not be as smart or as developed or as progressed as a year 13 would. As a result, this assumption may not be valid, as year 11s may not take their exams as seriously as year 13s. Perhaps try to link it back to the university thing. Year 13s are more likely to pass as they are taking it more seriously for university entrance. requirements. Okay. And they may not, I've got a typo up there, not sure what that was meant to be, but I'll leave it there. So that kind of wraps up what I was talking about. So just as an average, I think the year 11s probably aren't going to be as onto it or as motivated as the year 13 counterparts, which makes this assumption not really a good one. And that there was meant to be valid, wasn't it? Okay, so now onto assumption number 2. And we've got a similar vibe to think about it. So we've assumed that year 11s and year 13s, they've got similar snoring habits. And on the face of it, I don't think there anything is too majorly wrong with that assumption. I feel like kind of teenagers, you've all probably got the same likelihood of snoring. But there was a part of the previous question that caught my eye. So this kind of part down here. So we've got a group of 260 year 11 students from the same schools, sitting examinations. 127 of these year 11 students self-classify as snorers. So that self-classify part of it was really concerning. So that means they're kind of volunteering this information themselves, and we don't really have that information about the year 13s too. So I feel like the year 13 information is going to be a bit more reliable than this year 11 information. And because snoring, I think, would be seen as a bad thing, I feel like maybe some of the year 11s who do snore, maybe they've lied and they've said they've snored. Or vice versa, maybe they're in front of their friends, and maybe some friends are joking around saying they're big snorers just for a cheap laugh. So this self-classifying thing, I don't really like, and it doesn't give me any faith in the year 11 information. So these assumptions, so the assumptions about the snoring being the same for the year 11s and year 12s, may not be valid as the year, I'll keep spelling valid wrong, I did that before, didn't I? As the year 11 snoring data is self-classified. I imagine the year 11 data may be biased. How's about biased? Because being seen as a snorer is probably not a good thing. So without knowing the actual proportion of snorers, I'll be very hesitant in saying this is the case. Probably just carry on. So without knowing the actual year 11 snoring data, I would hesitate in using this assumption as part of any calculation, because I don't think it's a good assumption necessarily. Let's move this up just so we can see them a bit better. So hopefully that makes sense. So the first one was a big assumption that I think is just invalid. The second one maybe is right, maybe it's not right, but the fact that data is self-classified is very concerning, and I'd be very hesitant in actually relying on anything that comes from that second assumption. Okay, we are now on to question number 5. So just noting in the merit section, there was an II, and you needed to get that part and this triple I part to get your excellence mark. So we've got 3 social medias. We've got Instagram, Snapchat, and Facebook. Instagram reports that 80% of the users are from outside the US, which means the other 20% must be inside the US. Of the non-US users, 47.5% of them log in every day, and of the US users, 60% of people log in every day. So that's kind of all the data. Let's get into the question. So a probability model is developed based on the information provided. So all of this has been used to form some kind of probability model or calculation. Under this model, the probability of an Instagram user from the US logging in daily is 60%. Discuss why it might not be appropriate to apply this model to all types. They've capsed all types of US Instagram users. Okay, so they've basically generalized this 60% number. They've generalized it for everybody, but we've been asked, is that appropriate? Is every single person going to have a 60% chance of using Instagram on a daily basis? And I definitely not. So let's just start off with that. So this model may not be appropriate if applied to all types of, I'll just call it IG users in the US. And let's think of a couple of reasons why. So firstly, why wouldn't it be appropriate? The thing when I think of Instagram, I don't have Instagram because I'm not cool, but I feel like influencers and kind of cool people, we'll call it in quote marks, or the celebrities, they're very heavy on Instagram. And those people, absolutely no way 60% of the time they're going to be logging in daily. I would suggest they're logging in, 20, 30 times every single day because they're probably addicted to it as well. So the first thing I want to talk about, I'll get back to these in a bit more detail and I'll expand them out. So I probably want to talk about influencers and the fact they log in 20 times daily. No way that's going to be a 60% number. The second one is the flip side of that. I thought, are there any groups? So I know this group of people, the influencers, are going to be logging in every day no matter what. But are there going to be other people who won't be reliably logging in? And when I think of America, I know this is a bad perception and maybe it's a stereotype, but I do think there's quite a big homeless person rate. And I can't imagine all of those homeless people even have access to the internet on a daily basis. And because they don't have access to the internet on a daily basis, they're probably not going to be checking Instagram on a daily basis either. So the flip side of that is I think homeless people are going to have less access to the internet, and their probability of checking Instagram daily is definitely not going to be 60%. It's going to be 0% in some circumstances. So that's going to be the next paragraph, and I'm going to pad these all out. In a bit more detail. So that's kind of where my conversations want to go. So let's kind of pad out the first one. So firstly, social media, we'll put them influencers who make their money from IG would have a 100%, would have a 100% chance of checking their IG every day. In fact, I suspect some people would be logging in 20 to 30 plus times per day. So for these people, they would not have a 60% chance of logging in daily. Rather, it would be 100%. So that there discredits the use of 60% in those particular circumstances. So let's get rid of these. Do we now want to tackle that homeless one that we thought about? So I guess conversely is the word I want to use because it's kind of the opposite to that. Conversely, there may be a large portion, or there may be some, maybe some people in the US who do not have regular access to the internet and therefore Instagram. For example, homeless people and people in maybe rural areas of America may not have reliable access to the internet, which means they can't check IG even if they wanted to. So for these people, they would not have a 60% chance of logging into IG daily. Rather, it would be much lower. So that wraps up that chat that I've got there. Let me just put a comma by the so to get rid of the thing. Yeah, so I've kind of discussed why for some people it's going to be a lot lower. So for the influencers, 60% is way too low. They're going to be checking it, as I said, 20, 30 times a day plus. And then, on the other side of things, there are some people who just literally couldn't access the internet or Instagram if they wanted to. So 60% for them is also not going to work. Question number 6. This is the final question from all the excellence questions in the 2019 exam. Check the link in the bio for this sort of, or more of these questions. But I really like seeing questions like this. As soon as you see a big list of bullet points like this, it normally screams three-way table. So don't assume it's going to be. So as you're reading the question, we should be looking out for 3 different variables. And if that's the case, that matches and confirms what we're doing. So if a young person uses one of the social media sites, and that was, the Instagram, Snapchat, and Facebook that they mentioned in the previous question, they are likely to use the other sites as well. For a group of 300, we've got this information, and that confirms it 100%. So you see you got Snapchat, Instagram, Facebook, so that's going to be 3 variables. We've been asked, it is claimed that if a social media user selected from one of the surveyed is an Instagram user, they are twice as likely to use Snapchat over Facebook. So basically, we need to find what's the probability that they use Snapchat given they use Instagram. And we also need to find what's the probability that they use Facebook given they use Instagram. And then we need to probably do a relative risk because it says twice as likely. Also, actually says more than twice as likely. So we need a relative risk greater than 2 for that to be true. So our relative risk needs to be greater than 2, and then that will confirm the claim that was made. So let's go ahead and start drawing our table. So I'm going to draw my horizontal lines to start off with, and I'm going to use quite a big space here because I'm going to do some coding to help me out. So the first group here, so this is going to be, the first one referred to was Snapchat users. So let's put that as Snapchat. So we've got people who use Snapchat and people who don't use Snapchat. And then I'm going to chop this one up as well. And then we've got people who use Instagram and not Instagram users. And we're chopping the bottom one up as well. So Instagram people and not Instagram people. And then finally, Facebook's my only other one. So that will be the Facebook people and the not Facebook people. And then we've got room for all our totals kind of surrounding it. We kind of don't really need that space there, but we'll just leave it for now. So let's run through number by number, put them in its spot. So the first thing is there are 300 young adults. So that's going to be our grand total down the bottom, 300. So I've now used that bit of information there. 84 use all 3 sites. So we don't need to use any coding. That's going to be up here because it's Instagram, Facebook, and Snapchat. So it's one of each. So that's 84. So I've now used the 84 number. 12 of them use neither. So that's going to be not, and not. So that's going to be down here. So we've got 12 people who use none of them. We've got 207 use Snapchat. So the Snapchat group is up the top here. 207. And I can actually find out the not Snapchat group by doing 300 minus the 207 at this stage. And that's there's going to be 93. So I've used that number there. 195 of the Snapchat users also use Instagram. So this one's going to be a bit messy. So Snapchat and Instagram people. So we've got Snapchat and Instagram. So these people here have to be 195, don't they? So luckily we've already got one of them. So this box here is going to be 195 minus the 84. And that's going to be 111. So 1, 1, 1. So no codes yet needed, which is nice. So 94 Snapchat users were also Facebook. So the Facebook and Snapchat one are going to be 94. And that's really nice because we've got Snapchat and Facebook. So that means these 2 groups here are going to be 94, which means this one here has got to be 10. 116 use Instagram. So these 4 here all have to add to 116. So I don't have 2 of them, which means I can't figure it out. So what I'm going to do is I'm going to do my coding. I'm going to put a plus sign in each of these. And I'm just going to note down here, all the plus signs, they have to add 216, but we don't have all that information yet. And then finally, 163 use Facebook. So this total down the bottom, 163. I could figure out this one here by doing 300 minus 163, which is 137. Hopefully I'm not doing any math errors. And I've used up all the numbers now. So are there any that I can figure out? And I definitely need to figure out one of these plus signs before I can actually go ahead and figure that out. So it's going to be a bit of an issue. So the obvious one is I can figure out this top one here, I think. because all four of these need to add up to 207. So if I do 207 minus 111 minus 84 minus 10, that's going to get me to this number down here. And when I do all of that, I think I get to 2. So not many of them. So there are 2 people in this group. Now I can work down the not Facebook group because they've got to add to 137 and I only don't know this one in the middle. So 137 minus 12 minus 2 minus 111 is going to get me to that one in the middle there. And then when I do that, I get to 12 as well. That's really good because I can now figure out the plus sign ones. All these plus signs, as I said, have to add to 216. So 216 minus 12 minus 111 minus 84 is going to be that last plus sign down there. And that's going to get me to 9, I believe. And then finally, I can work down the Facebook column to figure out the last number, which over here is going to be 60. So big mess, but I've got my three-way table, which means I can go ahead and start figuring out all my calculations. So let's start over here. So my first part of the question, remember, was finding Snapchat given Instagram and then finding Facebook given Instagram. And then we wanted to move on to the relative risk part of it afterwards. So the probability that they have Snapchat given they have Instagram, that's going to be equal to, so the Instagram people are the only people we care about, and we know that's going to be all the plus signs, which came to 216, and remember that's in the question as well. So that's my denominator for both of my probabilities. Oh gosh, I'm deleting the wrong things by mistake. There you go. 216, and of these 216 people, how many of them use Snapchat? That's the 84 plus 111 up above, and that gets me to 195. So 195, I'm now going to convert that to a decimal, and I'm getting 0.9028. So roughly 90% of these people are going to have both Instagram and Snapchat. We're now going to calculate the probability that they have Facebook given they have Instagram. So same thing, my denominator has to be the number of Instagram users, which is still 216. And of these 16, this is a bit messy to see, but you got your Instagram and Facebook up here, and you've also got some more Instagram and Facebook people up here. So that means there's 93 of the Instagram users who also use Facebook. So that means my denominator or my numerator here is going to be 93. And when I convert that to a decimal, I got 0.4306, and that there had a 4dp around it. So we've got the two probabilities. We now need to find or calculate out that relative risk. So my relative risk, remember, it's always equal to the big probability divided by the little probability. So that's going to be 0.9028, and that there is going to be divided by 0.4306. And when I do that division, I'm getting 2.1, and that had a 1dp rounding. So that 2.1 definitely confirms that it's more than twice as likely, so it is greater than 2. So I now just need to kind of put that together in a sentence or two, just confirming that I agree with the claim. Okay, so this means that an Instagram user is 2.1 times more likely to have Snapchat than Facebook. So that kind of discusses the relative risk part of it. Now we've just got to make sure we just got to agree with the statement. This is more than twice as likely. So the claim is correct. And that wraps up that last question. So hopefully you found all these excellent questions useful. I know the video is really, really long. Don't stress too much because this three-way table, whilst I've done it from scratch, you would have had to do this in a previous maybe achieved on merit question in part I. So they don't, they won't take you as long as you think they would. So don't stress too much about timing. So thanks heaps for watching. If you need any other resources or whatever, just hit me up in the comments and I'll try to reply with anyone with questions.